In this video, we're going to talk about one of the most important concepts in AWS networking, Amazon VPC or Virtual Private Cloud. VPC is the foundation of networking in AWS. Every resource you create, whether it's an EC2 instance, a database, or a load balancer, must live inside a VPC to be operable and accessible. VPC is your private and logically isolated section of AWS Cloud where you have full control over networking, connectivity, and their security. As you move forward, you'll realize that AWS gives you multiple ways to design your VPC and get your resources working. The more you learn, the more you'll be able to fine-tune things better aligned with performance, efficiency, and security practices. And one more thing before we start. Just note that, think of a VPC like a puzzle, where each piece plays a crucial role in forming the complete picture of your network infrastructure. It's made up of many different components, but in this video we'll only focus on the most important networking ones you'll need to understand to create a basic but functional and secure environment for yourself in AWS. Okay, let's first start with VPC Boundary. The very first important thing that you know about VPCs is that VPCs are always tied to a specific region. This means if you want to deploy resources in multiple regions, you'll need to create separate VPCs inside each one, since a single VPC can never span across regions. By default, every AWS region comes with a default VPC. This default VPC already has the basic networking components set up for you. That's why you can launch and then access your resources ready to go without doing any particular networking configurations yourself. But in many real-world scenarios, you'll want to go beyond the default VPC and build your own custom VPC from scratch. This gives you full control. You can design your own IP ranges, decide how to separate subnets, and many things to help you with better aligning your architecture with best practices. One of the required inputs you'll need to define when creating a VPC is the VPC CIDR block. The CIDR block defines the IP address range that your VPC will use and operate. You can only use your CIDR block from the mentioned ranges. In our example, we used 10.0.0.0/16. This range determines how many IP addresses you'll have available and how you can divide them. Just note that, once you define a VPC CIDR block, you cannot change it later. This is why planning your IP address range properly at the very beginning of creating your VPC is so important. Make sure your CIDR block is large enough to support future growth. Next, there are subnets. Subnets are subdivisions of your VPC's CIDR block or IP address range. They are tied to a specific availability zone inside your region. Each subnet can be either public or private that allows you to organize and isolate your resources. The common practice is you usually break down the VPC CIDR block into smaller subnets for both public and private use. For example, if your VPC CIDR is 10.0.0.0/16, you could divide it into several /24 subnets, such as 10.0.1.0/24 and 10.0.2.0/24. These subnets can be used on your public subnets, one in AZA and one in AZB, and 10.0.11.0/24 and 10.0.12.0/24 for your private subnets, again, one for AZA and one for AZB. These IP prefixes can be whatever you choose. As long as they fit inside the larger VPC CIDR block, it's okay. In our example, we use 4 subnets, but you could define different prefixes and counts depending on your design and requirements. Resources that are created in a private subnet stay internal and have no internet access by default. And this approach is best for sensitive workloads or internal backed workloads. But resources in a public subnet are meant for internet-facing components, and they can connect to and be reached from the internet. How you divide your CIDR block depends on how many segments you'll need and how many AZs you want to utilize within the region. A good practice is to plan your subnets so that they are evenly distributed across multiple AZs for high availability, while also leaving a space in your CIDR range for future expansion. Next, we have route tables. A route table contains the set of rules that determines where network traffic should be directed. For example, a public subnet's route table usually includes a default route, which is 0.0.0.0/0, that points to the Internet Gateway or IGW, which we will cover in a second. And in contrast, a private subnet's route table typically only routes traffic internally within the VPC to keep resources isolated from the Internet. Each subnet must be associated with a route table to operate properly. It's also good to know that whenever you face network connectivity issues, route table is one of the things that you can double check to see if your changes introduce any missing or incorrect routes in that part. Alright, now getting back to the Internet Gateway that we just mentioned. Internet Gateway or IGW is the component that acts up as the bridge between your VPC and the Internet. Any traffic routed to an IGW have the ability to go out of your VPC to the public Internet. So that's the reason public subnets are configured with a default route to the IGW to access the Internet. After understanding IGW, another related component that you know about is Elastic IP Address or EIP. An elastic IP address is a static public IP address that you can allocate or reserve from AWS and then attach to your EC2 instances. First, you should know that, by default, public IP addresses assigned to your EC2 instances are dynamic, meaning they can change whenever you stop and start your instance. That may not be ideal if you need a consistent IP address. For example, you might need to whitelist the EC2 IP on a target system, allow access through a firewall. But if the IP keeps changing over time, those configurations will break and stop making sense. So elastic IPs are there to address this behavior. You can allocate a static IP from AWS and then attach it to your instance, ensuring it always has the same address even after reboots or stop starts. You can also detach the elastic IP and reattach it to another instance if needed, which makes failover and recovery much easier. In short, an EIP gives your resources a fixed and reliable identity on the Internet, unlike the default dynamic public IPs. As you can now see in the diagram, when the elastic IP is attached to the instance 1, all of its external communication is routed through that fixed IP address. While an Internet Gateway allows resources in public subnets to communicate directly with the Internet, resources in private subnets are intentionally isolated. However, you still may want to provide one-way Internet access for these servers in their outbound traffic. For example, you need to download software updates, pull container images, or many similar things that require Internet access for your private servers. So NAT Gateway is your solution in this case. NAT Gateway allows instances in your private subnets to initiate outbound traffic to the Internet, but prevents the Internet from directly initiating connections with those instances, just like a traditional NAT solution in your on-premises network. One good thing is that you can also attach elastic IPs to NAT gateways. This gives your outbound traffic a consistent public IP address, which is extremely useful. As you can now see in the diagram, all of our private EC2 instances follow the flow through the NAT gateway, and the attached EIP2 becomes their consistent public identity for outbound traffic. This means that no matter how many private instances you have, all of their internet requests will appear to originate from that single elastic IP. Alright, switching gears to security section. Let's take a look at security groups. Security groups are virtual firewalls that operate at the resource level. Security groups can control both inbound and outbound traffic for your resources. For example, you can define which IP address, which port number, or which protocol types are allowed on your inbound or outbound traffic. As you can now see in the diagram, we created a security group called SG1 and attached it to Instance 1. In this case, we've only allowed FTP or FTPS traffic from the specific source IP of 31.19.185.19/32, which we assume it's one of our trusted IPs that should be permitted to upload files to the server. In addition, we've allowed HTTP and HTTPS traffic from any external IPs, which effectively makes the server act as a public-facing web server, while still keeping other ports closed. It's very important for you to understand two key things about security groups. First, the default behavior in all security groups is deny all, meaning that you can't explicitly write any deny rules. You only write rules for the allowed traffic, and anything not declared will automatically be considered as deny. Second, security groups are stateful, meaning that once a connection is allowed in one direction, the return traffic is automatically allowed in the opposite direction, regardless of the other rules. This applies only to return traffic. So if you allow all outbound traffic but declare no inbound rules, your instance can still initiate outbound connections and successfully receive the responses. AWS always recommends that you follow the principle of least privilege, which insists on only granting the minimum access necessary for a resource to perform its tasks. For now, please just pay attention to the fact that you should never leave security groups wide open to the all traffic, and you should always use properly restricted rules in production environments. In addition to security groups, VPCs also support Network Access Control Lists, or NACLs. NACL is also a firewall operating at the subnet level and provide an extra layer of security. NACLs are more similar to traditional network access lists you may have seen in on-premises networking. Each rule has a numbered priority and they are evaluated in order. The evaluation stops as soon as a rule matches. Unlike security groups, NACLs support both allow and deny rules and actions, giving you more flexibility for subnet-wide restrictions. By default, every new subnet you create is automatically associated with a default NACL, which allows all inbound and all outbound traffic until you modify it. If you create a custom NACL, however, its default behavior is to deny all traffic in both directions until you explicitly add allow rules. For now, just understand the fact that NACLs are stateless while security groups are stateful. This means that with NACLs, you must explicitly configure both inbound and outbound rules since return traffic is not automatically allowed. You can use them when you need the broad subnet level policies, for example, blocking an entire IP address range from ever reaching any of your resources in your subnet, while leaving security groups to handle fine-grained instance-level access control. Alright, since we talked about different terms and a lot of terms here, let's recap and see what we've covered. A VPC is your private network boundary in AWS that exists inside a specific region. Subnets divide your VPC into public and private sections inside availability zones. Route tables define how traffic flows, and each subnet must be assigned to a route table. An Internet Gateway, or IGW, connects your VPC to the internet. Elastic IPs, or EIPs, are static public IP addresses that give resources a consistent internet identity. On a similar concept, NAT gateways enable private subnets to make outbound one-way internet connections. And on security terms, security groups protect individual resources at the resource level, and they are stateful and fine-grained. And at last, NACLs operate similarly to network layer firewalls, which are stateless. Now, I know this may feel like a lot to take in at once, and that's completely normal. Networking concepts can seem overwhelming in the beginning, but the more you review and revisit them, the clearer they'll become. And don't hesitate to rewatch this video, pause at the diagrams, and give yourself some time to connect the pieces. With practice, these ideas will start to feel more natural, and you get better at building and designing your own VPCs. Alright, that is it for this video, everyone. Thank you for watching, and please don't forget to subscribe to our YouTube channel, and I'll see you in the next video.